So good afternoon, everyone. Let me kick us off here. This is the next edition in our webinars. Today we're covering the question, how can a world generate and support life? Our speakers are Brittany Schmidt from Georgia Tech and Robin Wordsworth from the University of Chicago. And they have prepared a short presentation. After that, we'll take questions from you, and we'll have hopefully a rich online discussion. I'm sure there'll be one going on in the chat as well. There is a document for this, a white paper, that's on the main page of the astrobiologyfuture.org website. And immediately following this webinar, I will open that document up so that it's available publicly for comment. Currently, it's available publicly for viewing. Right after this webinar is over, I'll make it publicly available for comment. Thank you very much. And with no further ado, may I turn it over to the two of you?
Sure. So I just wanted to, before we started describing the document, just let everyone know that it's still a little bit rough. We've got a few changes that we want to make as a group. We were already affected by the shutdown because some of our major contributors were NASA employees. So we've been trying to adapt that pretty quickly. But anyways, it is a pleasure to be here to talk to you about what we've been working on. So I wanted to give you some of the background to the way a couple of these will work. When we were actually at the meeting out at Wallops, we had a group online and then also a group in person who were all interested in kind of the same topics. And a big point of what this group was working on was that we're getting to the point now where disciplinary investigations of planetary science or exoplanetary science or those related processes just aren't going to answer the questions that we need to answer in the next 10 years. And so instead of breaking up into an exoplanet group and a planetary group and a formation group, we really wanted to come together and work on those documents kind of in parallel and all together. So this is the first of what will end up being 4 documents. This one is how can a world generate and support life, which has some themes of some of the papers that you've already seen. There's also how can we search for, detect a habitable planet in our solar system, and how can we detect life in our own solar system, and then a final document on how we can detect habitability and life on other planets outside of the solar system, so that we have the same questions and the same themes that run through these documents kind of brought together by the same group of people, so that those fields are all interacting. So that's kind of how those documents go. So this is the first one because it's the one that we kind of developed the most. And both of us were going to share kind of what we've been working on there. So just to start off, I guess, basically the idea behind this particular document is that if you think about what makes a habitable planet, it's not just kind of a state of being. We're beyond just searching for water or just searching for oxygen or something like that. We really need to understand what it is that allows one to form in the first place, what allows one to evolve, what are the factors that actually contribute to its evolution, and then what are the factors that define habitability at present day, so that we can actually think about how to detect that now. So really, how can we look at other stages of planetary evolution that lead up to a habitable planet, and then how can we look at a planet today and assess whether it is habitable and whether it's inhabited. And those are different questions, but they're very, very related. So the mission statement that we had was to understand how life can get started and or survive on a world. It makes sense to have a good understanding of how the planet formed, how it has evolved, and its present geological state. Assuming that planets with kind of active geologic or environmental cycles are likely more relevant for present-day habitability than those which had it in the past. So it gives us maybe some directions to head as we think about where to study these planets. And so we're going to consider each of those kind of 3 fundamental areas as we go along. So the first area was what are the fundamental components and processes that allow a habitable or inhabited planet to work or to exist. And so in that sense, we really tried to boil it down to what are the exogenic factors or the formation factors that build the planet in the first place, which you probably heard about if you were on yesterday's telecon. There was a lot of study on that as well by another group. And then secondarily, what are the endogenic factors or the planetary factors that allow habitability to evolve? And so what we've tried to do here is to ask some leading questions that connect to themes of research and fundamental advances we think might be important for really understanding and assessing what's habitable and how you create it, or how it comes to evolve. So some of the examples of exogenic factors or factors outside the planet itself that might affect it. What is the initial inventory and distribution of volatiles and the oxidation state of the disk and of the planet, or the planetesimals that are actually building the planet? That kind of speaks to the amount of oxygen, the amount of volatile material, the amount of kind of those critical ingredients that we think are the hardest to get in certain areas in the disk. And so what is the state of the disk early on, and what can we say about early planetesimals that end up forming that system? What are the properties of the host star that are conducive to or prevent the formation of a habitable planet? So this is something that Robin probably thinks about a whole lot in his work, and in exoplanet work. I think we're thinking a lot about it now. What's the age of the star? What class of star? Are we talking about an M dwarf or a G star? Metallicity, there's still that question out there. How metallicity really might be a stellar marker of habitability. The activity of the star and perhaps the galactic neighborhood. What's the influence of cosmic rays and star-forming regions, things like that. So those are all also related to kind of the stellar environment. So, further, if you're looking at the age of the star, if you want to break it down into how stable that star is, or that kind of formation environment is to the preservation of a stable environment for the planet, its ocean, its atmosphere, the radiation it's enduring. So those are a little bit different than what ends up building the planet, but very similar. Again, what are the abundant elements in the disk and their effect on planet formation? So getting more towards, if there is a more carbon-rich system, is that really a relevant system? Do you have enough carbon, oxygen? Do you have enough magnesium and silicon? Those types of factors. And what are the isotopic evolution of those materials? And then, of course, something we think about a lot, which is the early dynamic environment on the planet. Since we know that we've had periods of potentially heavier bombardment in the history of the Earth and of other planets, what role does that have? Is it delivering volatile material? Is it creating mass extinctions? Is it making the planet more or less habitable? And is that required in order to have a habitable planet? So I don't know if, Robin, did you have anything to add to that section?
Yeah, so I guess it should be clear from this slide and from the rest of the document as we continue as well, just the extensive links that this topic has really to the rest of what's been going on in the astrobiology roadmap. And in particular, I guess yesterday there was a discussion about how do you form habitable systems, and this slide is closely related to that and interlinked with it. But nonetheless, we feel that it's really important to have this as a separate document so that it can make some kind of attempt, as Brittany was saying, to tie these together and have integrated approach to answering kind of some of the basic things about habitability.
Yeah, I think hopefully it focuses it a little bit, or it allows us, even if these documents end up being several distinct documents, then, or distinct parts of the eventual roadmap, it at least gives us kind of a thematic connection so we can think about how those all interact to form it. So, moving on to the next one, the next slide that we had was endogenic factors. So when I'm saying endogenic factors, is probably a better word for it. It's probably, planetary factors. So basically, things like, what is the size of the planet? It might seem like that doesn't have a huge effect, but as we think about the effect of gravity on plate strength, on convection, the amount of the overall size and dynamics of the planet, then become very important. What is the inventory, distribution, and role of critical elements and minerals within the planet's interior? So, for instance, when you're separating out the Earth's core and you have lithophile and siderophile elements, does it lock too much of one material away? If you have a giant core on another planet, does that mean that more or less of the biorelevant material ends up locked away, where it's not necessarily relevant anymore to life as we might know it, or at least be able to detect it? Do you have radiogenic nuclides for continuing heat? A small core, you might not have it. So someplace like Mars that may have expended much of its radiogenic heat. Where does the water go? And what about things like phosphorus or something like that? What happens to those minerals as the planet is forming? I'm sorry, minerals, those elements as the planet is forming. We called out here, what is the role of core formation in habitability? That's been thought about as being important for several reasons. One I just described, the partitioning of elements into the interior of the planet that maybe removes them from being accessible on the surface. But in addition, factors like the generation of a dynamo, a magnetic field that might protect the planet as well. So is there a distinct, do you need a convecting iron core in order to sustain habitability? So do you need to form that in the first place? There's a lot of questions out there as to whether Venus or Mars, for instance, in our own solar system, or super Earths, where the core may be so hot that there's really no dynamo action, or that you have a different type of interior, then it may be more or less difficult to have what's required to support life on that planet. What governs the evolution of a world's interior and its effect on its habitability? So the total heat rate. So this is getting, it's related to the size of the planet, but it's also related to its radiogenic inventory. How important are those? And where does mantle, kind of mantle and surface cycling, what effect is that having? Are you locking material away or bringing it back up to the surface, or continually refreshing a biosphere? Something like that. What are the sources of energy inside the planet? Radiogenic heating, tidal heating, accretionary heat, differentiation, tectonism, and then additionally, the chemical reactions. If you have exothermic or endothermic reactions, then those both play a role in how a particular environment would evolve as a potential supporter of habitability or of life. What's the function of plate tectonics or a similar process? There's a lot of fundamental research going on right now in how plate tectonics operates here, part of the weathering cycle, part of sedimentation, part of the hydrologic cycle, but then also its effect on other planets as a function of chemistry, as a function of parameters inside the planet, of atmosphere, things like that. So how really does that system work, and what's its utility? More than just saying, is plate tectonics relevant, or is plate tectonics important to habitability? Let's understand why. What really is that process doing? What's the utility of it, so that we might better assess if a similar process might be able to do a similar thing on another planet. And then what is the role of geochemical processes on habitability? Oh, go ahead.
I was just going to add to that as well. I guess something really to emphasize is the link between volatile cycling and plate tectonics in terms of the role of water. It's kind of, for me as an atmospheric scientist, it's particularly fascinating to think about the role that water is cycling into the mantle and how that evolves in the planet over time, linked in with habitability. I mean, we traditionally think of water as being a fundamental thing that's necessary for all life, and kind of leave it at that. But the way that it interacts with the deep interior, and for example, mantle viscosity can be affected by increasing H2O amounts, it's really an example of how about the volatile cycle in tandem with what the dynamics of the deep interior is doing is a really fascinating question.
Yeah, I'm noticing Dave Desmarais is adding some comments as well. He's said a major effect of core formation and mantle structure, partitioning of redox-sensitive elements, which in turn affect redox state of the crust. Yeah, so that's kind of what we're getting at, is what really is the utility of those processes? Not necessarily do we have to have plate tectonics itself, or do we have to have a weathering cycle that's an atmosphere, a water rock, or a weathering of silicates, or if there's what's the role of that? And he's pointing out that the oxidation state of the mantle and the crust is highly affected by processes like that. And the thermal state of the mantle also affects partitioning of volatiles between the mantle and the surface environment, right? As we think about, volcanism, the rate of volcanism on a planet early on, that's affected by these geologic cycles, by the volatility of the mantle, the water composition, and so that affects the atmosphere. So thinking about those as cycles and as processes that can couple together, and that link studies between what might be considered disciplinary fields. What's great about it is that an open-ended question like that might allow a geochemist and a thermal modeler and a meteoriticist to get together and assess the habitability of a planet in a more, holistic sense. So hopefully those give you kind of a feeling of the direction that we went. And this is just kind of, this particular portion is focused on how a planet forms. So what's its early state? How much of that activity is going on to form it? So, Robin, did you have anything else to add to that section?
No, just to reinforce your point again, I think about what we were really trying to get across with this document is the interdisciplinary nature of these questions, and how encouraging increased collaboration between interior people and atmospheres people, and even those who work on things like escape questions in the future is really, we think, going to be a really powerful way forward.
Yeah, I think I forgot to mention at the beginning, too, that we had a group of predominantly kind of exoplanet detection people, a group of exoplanet modelers. We had some biomarker folks. I work on asteroids and icy planets. We had a few ice ocean or kind of ocean planet people. So we've been thinking about, and then obviously Dave and the group that works a lot on Martian habitability. We really didn't want a document that said, what do we ask on Mars, and what do we ask on Europa, and what do we ask on exoplanets? We wanted one that says, how do we ask this about planets, and then apply it. So that's where we're going for that. And you'll see those themes connect between the next parts of the document. So that's kind of more the formation of the planet. And then the second section is, what are the fundamental ingredients and processes that define a presently habitable environment? And here's where we broke it up a little bit, just so that we could ask some specifically targeted questions at some of the major fields of research. And so we've kind of broken it up into terrestrial type planets. Now this is Mars, Earth, Venus, super Earths, smaller Earths. So we're talking about more terrestrial objects. And then the second one, we have things that are perhaps a little bit of a stretch. So icy planets, ice ocean planets, perhaps some of the small bodies in the solar system, what's their role? And how can we relate questions about terrestrial planets, Mars, the Earth, Venus, exoplanets, or super Earths, to questions about the icy satellites, about the asteroid belt, about ocean worlds, about water worlds in exoplanetary systems. So that's what this one should focus on a little bit. So to kick off the terrestrial planet ones, actually, did you want to take a go at it, Robin?
Sure. You put the slides together, but I'm pretty familiar with the material. I'll take it from here. So for terrestrial planets, we were interested. First of all, as Brittany was saying with the point in the last slide about the mantle cycling and how it affects the volatile budget, clearly through outgassing to the atmosphere, that's going to be a fundamental determinant of the atmospheric composition as well. So we know for terrestrial planets what kind of geophysical cycles are going to be active and how they're going to influence both the atmospheric composition and the availability of biorelevant compounds. So I don't know, the changing redox state of the atmosphere versus the surface, whether the atmosphere is in equilibrium, whether the surface is in equilibrium, and how that evolves over time. And after that, the timescale for which the planet may be inhabited. So not just thinking about stationary states, but how the planet evolves over time and how the habitability can change over time as a result. So the internal heat budget, is that going to change as a result of volcanic processes or dynamical processes like we were talking about in the last slide? How's the greenhouse effect of the atmosphere going to change over time as a result of its changing composition? And finally, questions like, is a magnetic field necessary for the habitability of the planet? Or more generally, the changing solar terrestrial environment over time, how is that going to influence atmospheric escape processes or the XUV and UV environment of the surface? And is that going to be something that causes changes in the planetary habitability? So
yeah, I think this is also like the Mars question, or the highly related to what we're doing on Mars as well, right? So, is Mars currently habitable? Was Mars habitable? What were the timescales? This is places where dynamic involvement or evolution might be effective. Things like Milankovitch cycles would affect the timescale over which the planet is inhabited, and then the thermal budget as well, contributing to, is that planet habitable now versus was it ever? And so as we ask those questions about present day habitability, that becomes important. So go ahead.
I think that ties in directly as well to the question of global versus local habitability, and say, like for the case of Mars, can you have a situation where you have almost no surface habitability, but niches preserved below the surface where that becomes possible? If you're thinking about the planet evolving in time, it becomes basically essential to start thinking about spatial distributions and habitability as well. So moving on from that, we wanted to talk about, of course, the definition of the traditional habitable zone and think about the boundaries of that, in both in the classical sense, or if we're considering, say, for the outer edge, more exotic atmospheric scenarios such as reducing or hydrogen-rich atmospheres. We want to think about issues such as whether a planet has a prebiotic environment that's conducive to biology, and again, this ties into the redox state of the atmosphere. Do we have either atmospheric or subsurface chemistry, which is conducive to formation of a lot of prebiotic molecules? And if we're imagining planetary evolution in general, can we start to get a sense of statistically how common these kind of situations should be? And getting into even more thorny issues from there, questions such as what kind of biochemical systems on these planets could you get? The available polymers or metabolic processes, and moving on from there, getting really into prebiotic chemistry, like for a given starting atmospheric composition, what kind of complex chemistry could emerge?
I think.
Want to add something to that, Brittany?
Yeah, I was going to say the other thing to think about. This is also a deep biosphere question, right? This is, do you need a surface, a habitable surface, or can you be living in the subsurface? Are you using chemosynthesis? Are you using radiogenic elements as your source of energy? So this is the thinking about the present day state of the planet. What might a biological pathway be like, so that we can look for evidence of that? If we're always looking for respiration, we may never answer the question. So that's kind of the direct link, I would think, for trying to think about how even a terrestrial planet and alternative metabolism would work. Not really just hand waving something into existence, but thinking about how a different chemical system might be able to accomplish the same tasks as ours does. So that's pretty much what I had for that one. Yeah, so Dave was also chiming in a little bit, saying availability depends not only on the abundance of a key element, but also its chemical state. So redox state makes a difference. And heat flow likely affects the extent of habitable environment. So things like, that's that boundary, the habitable zone inside the planet. Is it the surface? Is it the subsurface? Something in there.
Yeah, I guess the availability question ties in directly to delivery rate as well. So if you're thinking in terms of cytophile elements are delivered through a late veneer, or again, the formation properties of the system, it's another.
Yeah.
It all emphasizes yet again the fact that you have to think about the evolving planet in terms of coupling between huge varieties of different processes. Do you want to take over the next slide?
Sure. So we've got this basically set up for the terrestrial planets, and using those as a jumping off point for other types of planets. And so the next part was ice ocean planets, or ice and ocean planets. So what are the fundamental ingredients and processes here that might work in a similar way? We realize that that's a different situation. In many ways, an ocean planet or even an ice ocean planet has a lot in common with the Earth at present. A global water layer is certainly a great thing to have, but how does that change things like mineralogy? So we had identified some sub questions, and these are things that apply inside the solar system to places like Europa, to places like Titan, to places like Enceladus, to Ceres, to the Kuiper Belt, so to Pluto, Charon, to Triton, any of those objects where the ice and the ocean might be a really interesting and analogous system to what we have here on Earth or in a terrestrially habitable planet. So the first basic question that we wanted to ask in this direction is, how might processes on these planets mimic those on Earth or a terrestrial planet to sustain habitability? So basically, this is taking the process analog mentality, which is, if we understand the utility of the processes on the terrestrial planets that we understand better, since we live on one and can experience one directly, then can we relate that to the utility of a process on an icy planet? So a really good example would be something like Europa or Enceladus or Titan, where you've got an icy mantle that may or may not be recycling. How does that recycling work? On an ocean planet, does that work? Do you get oceanic crust subduction so that you've got a recycling mantle despite not having any continental land masses? So what is the nature of the hydrosphere on the ice or ocean planet? So that's things like composition. Are there high pressure ices at the bottom? That's a big question for icy planets in this solar system, for things like Ganymede and Titan that are big enough to have kind of massive gravity and high pressure ices. And then even more importantly, as we think about ocean worlds around other stars, even Earth-sized worlds, that pressure environment at the bottom of a global ocean on an ocean planet might be very, very different and conducive to high pressure ices. Is there something that disrupts that? Is there something that makes that habitable, or does that make it uninhabitable by cutting off interactions between the water body and the silicate interior? What is the effect of mineralogy on a planet if there is no rock and atmosphere cycle, right? So we know that weathering and sedimentation and that our tectonic cycles have a lot to do with the mineralogy of the planet itself, and that should be true on an ocean planet as well. But how does it operate when you don't have that surface interaction necessarily? How does geology work on these worlds? This is just a fundamental question. Can you have subduction in ice? So actually, I was at the Geological Society of America yesterday, and I saw just an absolutely phenomenal talk on evidence for subduction on Europa. Very cool. So does that happen? Is it even possible? How does a geologic system work on an ocean planet? The whole question, do you have subduction in an oceanic crust or an entirely oceanic crust? What is the heat budget within this ice or ocean world? Oh, did you want to say? Yeah.
Yeah, so one point to kind of reinforce what you're saying on this is like you're talking about in the context in the solar system is obviously strong because we have examples of worlds like Europa where we know they're extremely aged, but it's starting to become increasingly clear from the exoplanet perspective as well, that both from the chemical theories of system formation and from observations suggesting a whole bunch of planets with really quite low densities. We really do expect a whole lot of planets that are approximately Earth-like orbits that have much greater H2O inventories. So if we're really thinking about searching for Earth-like planets in the habitable zone, there's strong theoretical reasons to believe that tons of these are going to have very water-rich inventories. So it's of clear astrobiological motivation to start to untangle some of how processes could occur on these systems.
Yeah, I think that's also it's a major focus of the JUICE mission, right? Of ESA's largest class mission is to. They're actually the purpose or part of the purpose of the mission is to connect Ganymede to potential exoplanetary environments where you've got a giant planet with or a very large ice ocean system. High volatile inventory, and its own magnetic field and processes that we expect on terrestrial planets. So that's an example of where there's cross-cutting relationships between extrasolar and solar system studies. So we've got questions like, what is the heat budget within the ice or ocean world? What's the role of oceanic composition and circulation? Does it mix materials? Does it affect heat transfer? How does it make the planet work? Is there an atmosphere, and how does it exchange with the ocean and interior? So this is a Titan or an ocean world with an atmosphere question for exoplanet systems. Is there going to be an oxygen atmosphere on top of an icy planet or an ocean planet, and how would that work? And how would it be different? What are the potential reservoirs of prebiotic, biorelevant, or biological materials? And this kind of actually, so Dave's making a comment, are biological processes really viable at the surfaces of ice ocean worlds? It says low temperature and slow organic kinetics in these cold environments raises a question. Of course, that's up on the surface, not in the interior. So can biochemical processes make any headway against destructive processes at the surface? So actually, I think Dave's making a great question or a great point that it seems that the subsurface environments offer the greatest promise, perhaps even on Titan, and that may be true, depending on where you're at. If you don't have a surface environment that's really conducive to that, and I think that's probably more of it in our solar system, but that would affect an ocean planet, an ice planet, in fact, even a terrestrial planet around, close into another star. So same question, that we had in the terrestrial planets, what might a biochemical system on this planet look like? So does anything change fundamentally when you're mostly ocean or you've got, you don't have continental land masses or something like that? And this is probably super relevant for Titan and for the outer solar system where there's a heavy inventory of other volatile species that might be helpful. Do they create, on Titan, can you have a different, a weird life on Titan? Are tholins a big important factor? Something like that. And then that might also affect planets around other stars as well. And then I thought a really cool question that has been heard probably time and time again, which is, could late stellar stage warming initiate origins of life or initiate a second era of bioactivity on a planet like Titan, on an ice planet around another star? Is there a way to do that that makes it relevant at one point and not at another? So that's probably more of a formation question, really, but it's something to think about. So,
and it's like, I think again, this concept of habitability evolving over time, and rather than trying to think, is there a habitable planet in this location or is it uninhabitable? Thinking more in an evolutionary sense, and so even for environments that are very exotic for life currently, like Titan, at the end of stellar evolution, if they can transform quite significantly. I wanted to add just one thing to that slide as well, which is the links between this kind of stuff you're talking about here. And some of you may have seen Ty Robinson's presentation, I guess about a week ago, on the evolution of the Earth with time. So we're talking about ice, ocean, planets in the solar system, but there's pretty good evidence now that the Earth itself is in fact a snowball planet at one time. And so not just a question of planets being extremely water-rich or water-poor and being in one state or the other. The kind of volatile cycles we were talking about earlier, specifically CO2 outgassing on the Earth, can, when you get modifications to that, you can get transformation from an ice ocean planet to a habitable world and back again. So there's, it really seems apparent that there's ways in which habitable planets can become uninhabitable and back again. And we have to understand how the volatile cycles work, both in cases like the Earth and in the more exotic cases of the icy planets in the outer solar system, in order to understand how habitability is going to transition from one state to another in general.
Yeah, I forgot to mention that entirely. It's kind of a neat way to think about it. You know, if did complexity, for instance, on Earth have something to do with periods of extreme climate that we might be observing right now on other places? You know, so there's ways to connect all of these studies as well, not just to assess the present day habitability of individual planets, but maybe they all inform each other. So that's kind of the lesson that we wanted to, not the lesson, but the kind of the theme that we wanted to use to connect these studies, so that we might have, so we start using the same literature and we start using the same questions to address all of these planets, so that we have a better understanding of all of them. So I think that's pretty much it. I mean, there's more to the document. We're adding some kind of directions based on these questions. So these questions are meant to kind of be provocative for different fields of research to address. And then there's some directions in the document as well for things that we might be able to identify over the next 10 years to make some progress. I'm not sure that we'll actually, the document isn't static yet. We've been still working on it. So I'm not sure how it's definitely in a state of flux, but the first 4 pages on that document right now kind of give you these questions, and then the 5th page talks a little bit about thinking about priorities, and then after that is the background material that we were using or that we were working from. And I wanted to call out that in the original document, we actually pulled from several source documents. So the paper that is based on background information and questions that were formulated by the community and then also by those who were at Wallops. And so the paper contained material from the search for life on other worlds in our solar system. How would we remotely find and identify an inhabited planet? Did life ever arise on Mars? Does life exist on Mars today? Are there organisms on Mars using perchlorate as an electron acceptor? Probably too specific for an actual item in the roadmap, but a very important point about alternative pathways. And that's the same thing for things like Titan or extreme environments. So Titan as an astrobiological target. How can a world generate support life? And how can we use remote characterization to understand such worlds? So those are all the documents that we actually pulled material from. So there was a lot of icy planet stuff, there was a lot of Martian stuff, there was a lot of exoplanet work, and a lot of detection stuff that we were trying to incorporate to start asking the right questions that should spur along maybe the next decade of research, which is the goal of all of these documents in the first place. So were there any questions or comments that folks had, or?
Yeah, should we just open it up to discussion in general now?
Yeah, thank you guys very much. We have just about 15 minutes left to the top of the hour, so questions and comments. I think everybody is unmuted by default, so all you have to do is speak up, or if you've muted yourself, you can unmute using *6. We'd love to hear your comments, thoughts, and questions.
I had a couple of comments in the chat section.
Is that David?
Yeah, this is Dave Demery, sorry. And that is, this is just a general comment for all these papers, and that is that there's all that rich material in the background section, and if it somehow could be made more accessible by organizing into a series of little short essays, I mean, basically using the language that's there already, but organizing it under titles that you can easily refer to after you've looked at the front part of the document. That way you capture all the richness and make it more accessible. Just a thought. I'm getting ideas about how we might do another section here.
Yeah, I mean, there's a plan with the document to, especially the last few pages, to make it less of a series of bullet points and more kind of in prose form, like you're talking about. And I guess that's a pretty good way to do it. Just have little bold headings and a paragraph or so on each concept, and not necessarily organize it any further than that, because I guess that should be clear from our presentation. There's just such a wide array of issues here that it's perhaps not even appropriate at this stage to try and have an extremely organized format. It's more a bunch of a two-page summary, which Brittany's done a good job of putting together, and then after that, simply a collection of ideas of interesting future research directions. Any general questions about the
Is there any specific type of...
I'll chime in. Yeah, Brittany, Robin, thanks for presenting all this stuff. It's a lot of material, a lot of exciting stuff. This is Steve Vance, by the way. Something that comes through in all this is, in my mind, is wondering what of these processes might be inferred from signatures from exoplanet atmospheres, and how much of that is already a topic of conversation within the exoplanet community?
Well, in terms of atmospheric signatures, it like clearly the big question for all of this is how you can construct a model where you have an understanding of what's going in the deep interior, and how that couples with volatile cycling and changes the atmospheric composition over time. And I think that a very unsolved question at the moment is whether it's in fact possible to get unique circumstances where you can look at the atmospheric composition and say you definitely have this type of interior composition, or whether the dependence on formation factors, for example, is so high that you basically have to do observations in a more statistical sense. But what I think certainly is true is that in the coming decades there's going to be the possibility, certainly for planets quite close into their host stars, there's statistics on basic constituents of the atmosphere, maybe not their actual quantities, but in general just whether the basic atmospheric components should be retrievable. And then from there it's a question of whether that can be extended out to the kind of potentially habitable cases we're talking about, which will require more ambitious missions in the future. And then from there, I would say the grand challenging sense of planetary exoplanet physics on the theoretical side is working out whether we can put all these different components together that we've been talking about in terms of escape, interior modeling, atmospheric evolution, and have a kind of picture where you can see a spectral signature of the atmosphere and then say something about how the planet evolves over time. I don't think anyone knows the answer to that yet, but it clearly is what has to be worked on to deepen understanding in the future.
Cool, thanks.
Yeah, so Sean. Okay.
I think we were all just about to point out Sean's comment.
Yeah.
I'm just reading it.
So I think that's a good point. Little information, but for lots of planets, can we do something for habitability? And I think that's, and actually that works, I think, in the solar system as well. I mean, the small body populations for sure, we're asking the same questions of a whole lot of things with a little bit of information. You know, we're trying to move forward on what does it mean that there's an entire class of asteroids and it's only on that class that we see magnetite. In the Kuiper belt was the actual Like, what is a red surface telling you? Does that mean that there's geologic activity on the planet, or does it mean that there was stuff on top of it? So I think there's solutions to that question as well, that small amounts of information in large data sets can actually provide a lot of information. Probably a lot of, at least on the formation side, on habitability. I think that it's also possible that would kind of spur on some rethinking of the measurements we take, right? Analogous to what happened to the exoplanet searches, right? To do to look at Doppler shift, or to look at so I think that thinking about what you can do with very little information is actually helpful.
Well, yeah, it's funny to hear you say for the solar system that you can do that kind of analysis, because I'm always used to thinking about Earth, Mars, very small data sets, or like only a very small number of planets, but planets where you can get large amounts of information. And so a lot of exoplanet people are excited about the future where we will be able to do statistics for the very first time. But I guess it's true that that's already possible in the solar system. It just depends on which bodies you're looking at.
Yeah, and I think it's one of the examples of where the communities don't talk enough. I think there's a lot of that. I'm hoping that the next decade of planetary research is one where exoplanet stuff isn't all published in APCHE and planetary stuff isn't all published in Icarus, so that we're not, and then that we're no longer ignoring the geologic, or not ignoring, but underusing geologic geology journals. So, we've seen that in the debates about plate tectonics. We've seen it in the debates about the evolution of gas giant planets and all of that, and satellite systems and icy worlds. And we see the reinvention of the wheel. And so hopefully, if we're all communicating through the roadmap and we ask the right questions, then maybe we can kind of fix that, and we can all jump forward a decade of progress instead of reinventing each other's work all the time.
Yeah, I think we're absolutely all in agreement on that. And hopefully we've emphasized that in the document as well, just the strength of an interdisciplinary approach to these kind of problems.
Hi, this is Avi Mandel at NASA Goddard. Something from an exoplanet observation perspective, someone who observes exoplanets with the current limited data sets that we have, one of the major problems from models is that the degeneracies between different models seem to be very difficult to work with. And I think, from an observer, encouraging modelers to think about things like, what are ways to break degeneracies between a number of these very complicated and difficult issues that you've laid out through this presentation? So,
I think that's actually a really good point, and we should think about that, because we've got to do. We really need to work on that section that says the next 10 years priorities. And I think that may be a way, kind of a connective theme, is that there's a lot of that information out there. It's just not necessarily said in a way that's accessible to someone who's not an expert in that community. Right? So that's part of what the NAI nodes are trying to do, is trying to break some of that, break down some of those barriers between things. And I think you're right. So I think we each have it on ourselves to try to communicate better with our colleagues that work on different things, what we need from them and what we can offer them. It's amazing how slow that process can be. The asteroid and meteorite community, for instance, they talk to each other about certain things, but certainly don't talk enough, and they're talking about pieces of each other, right? So that's an example, and I think that that's a really good point, and perhaps some direction for work on those priorities.
This is Sean. I'll actually chime in with my voice this time. I totally agree with what Avi just said and what Brittany said in response. And I often look to the Earth community, the Earth sciences community, because they've done a great job looking at model degeneracies and quantifying uncertainties in their model. And one of the tools they've done for that, despite having even more models than we do, at least more GCMs, is they've done a great job of intermodel comparison. And that's something I think we can learn a lesson from and start doing more of that, whether it's the 1D models that have historically been employed for extrasolar planets, or the 3D general circulation models that in the last 10 years or so have been ramped up for solar system objects.
I just missed the last 5 minutes or so of the discussion. Could anyone just summarize for me really quickly what you were talking about? I just cut out when Abby was posing a question about exoplanets.
Yeah, he was just saying that as an exoplanet observer, he'd like for some of the modelers to hopefully help out in determining what observations they could make, or at least in breaking some of the degeneracy between those models, because they can be so complicated. So I think that, and so we're basically just commenting on that. And I was giving some examples from for some solar system work, and then Sean as well.
Yeah, I totally agree. That's an important goal. I think that we need to be realistic about the complexities and about, in the short term, how possible it's going to be to really constrain cases. Because I mean, especially for some of the more exotic super Earth cases, we're really just at the very beginning of understanding what kind of atmospheric composition could be possible. So, for example, when the redox state of the atmosphere, when the atmosphere becomes more hydrogen-rich, how the volatile cycling changes, or water-rich, and how things change in the deep interior. But having said that, it's such a fascinating problem. I think that it's clearly going to attract a lot more research interest in the coming years. And I think if the astrobiology roadmap can kind of focus some of those objectives of habitability, that's going to be a really positive outcome.
Yeah, I was also saying that I thought that was a theme we try to use to improve the directions for the next 10 years part of the document. So to continue that kind of breakdown of disciplinarity.
One thing I'd like to mention, and that is, as you compare the priorities for exoplanets with our own solar system, is just exploring the space about the numbers of pixels you have across the surface of the planet. And and of course in our solar system we can put a lot of pixels across the surface of the planet, but how many and the resolution and what you can do at those various resolutions clearly affects the data that you get back. And for example, somebody just made a comment that Titan might have life at the surface if you had hot springs or something. Well, what is it that astrobiology needs to advocate and support over the next 10 years to sort of enhance our ability to do remote sensing in ways that really address where we would go, where we would explore to do that? So yeah, I think that's one area that could bear some comment. Just, and maybe that's for the next thing that we're talking about here, but, namely how do you search for habitable environments? But I think in this group, saying something about the consequence of these processes that you've talked about in terms of features at the surface would give an entree to those of us next week in terms of how we would try to find those things.
Yeah.
If you caught the gist of that or not, but this idea
yeah,
about...
No,
yeah, go ahead. No,
I was going to say that was kind of the original reason that we combined all these groups in the first place, was that we were going, okay, well, one group is working on what is habitability, and then the next group is working on how to detect that, and we're not trying to detect the same thing, then it doesn't really work. And so that's why we kind of combined them all. So I think, hopefully that connective tissue still runs pretty deep. I think that's a really good point, because if you ask the right questions about the planet, then maybe you can get out the observables.
Yeah. Anyway, this white paper here is going to give the handles for the next one to, okay, given what you guys have said would be the nature of the habitable place, how should we explore that? What's the most effective exploration strategy?
And as we head here to the top of the hour, I think I'll use that as my segue to say next week on Wednesday and Thursday, we're looking at how to identify habitable planets in our solar system and then beyond our solar system. I have gone ahead and made the document available for public commenting, so everybody can find that document and leave comments on it. And I'd like to thank our speakers today and our audience for your participation, the rich conversation. And if there's nothing else to add from our two speakers, I think we'll call it a webinar.
Yeah.
All right.
Thank you.
Great. Thanks everyone.
Thanks, everyone. Bye-bye.
Happy Halloween.
Happy Halloween, yeah.